Good morning, everyone. My name is Kyle Lake. I'm an application engineer with Oasis Sales, and today we'll be talking about how we can run Valor and HyperLynx rules directly within the Xpedition Layout environment in order to quickly identify any issues that you may have. Okay, so today we will cover, and hopefully you'll learn, how to set up your board for simulation directly within the Xpedition Layout space, and how to start or invoke those rules from either the Valor NPI or the HyperLynx client directly within that Xpedition Layout space. So we'll be able to run simulations from predefined checks on the board, so we can define voltage drop or PI effects. We can look for certain causes to EMI issues, and then we can also look for assembly or manufacturing checks with the Valor NPI tool. And we'll be able to review those hazards and cross-probe directly into the layout tool where those hazards exist, all in Xpedition Layout. So this can be a very powerful and easy to use solution. Before we hop right into the meat of things, let's just talk a little bit about Oasis Sales if you're unfamiliar. Again, I am an application engineer that works for Oasis Sales, and Oasis Sales is a Mentor Graphics premier partner and has been for over 18 years. So we are certified distributor or reseller in the states that you see down below. Our territory is in the Midwest, and we offer solutions from FPGA design and verification to printed circuit board design, as well as any type of electronic simulation, including thermal. Okay, so if you have any questions on any of those tools, we would be more than happy to help you out with that if you reside in one of those states below. We also are paired during this webinar series with TriLogic, and TriLogic is our counterpart. They are also a reseller, and they are based in the New England area and service all of the East Coast. So they have been a reseller with Mentor Graphics for over 30 years, and they are happy to provide solutions from Mentor Graphics as well as Omnify for data management capabilities. All right, so both of us are now happy to be a Mentor Graphics, now a Siemens company reseller. So we're continuing to provide solutions to our customers and helping them find the best tools that will enable to meet their design requirements. Graphical representation here of our respective territories. Again, if you reside in that Midwest or Northwest section of the country, Oasis would be your reseller, and if you reside on the East Coast or Southeast, TriLogic would be your reseller. So if you have any questions on what we see today, please feel free to reach out to me, and I can definitely get you in contact with the correct salesperson or technical resource for you. If you like what you see today and would like to see more of what we've done in the past, please feel free to check out our website or our YouTube channel, where you can find all of our archived webinars. So we have all of our archived webinars, such as HyperLynx, PAD Standard Plus, PADS, or Xpedition specific. So hopefully you'll be able to find what you're looking for directly on there. Also, you can visit trilogic.com, and they have a lot of good technical resources on their website as well. I would like to throw this out there just for a next save the date of my next webinar that I will be hosting. That's going to be about a month from today, which will be Thursday, December 6th, same time. And we will be talking about multi-board design with Systems Designer and how we can design multi-board systems within the Xpedition environment. Here's my contact information. If you do want to take a quick jot that down or a screenshot of that, I'm always happy to answer questions, possibly set up a further demo so we can talk about the topics that we discussed today a little bit further. Or if you need evaluation info or any pricing information, I can definitely get you in contact with the correct person for that. So please feel free to reach out to me for any need you have for Mentor Graphics tools. If you do have questions during this, I'll do my best to get to all of the relevant questions during the webinar. I won't get to all of them, and if I don't, I will follow up with you shortly. But please use the chat dialog box that you hopefully will see in the GoToMeeting client. Okay, so there's a little chat dialog box. Just enter your message in there. You can have it send just to me, and hopefully I'll get to that during the webinar. Also, a quick note is that this session is being recorded, and it's going to be up on our website within the next 48 hours, and a link will be sent to you with just some more information on what we covered today. Okay, so without further ado, let's go hop into our webinar today. And again, we're going to be talking about how we can run Valor and HyperLynx rules directly within the Xpedition Layout space. So today is an interesting topic because we're going to be talking about essentially 3 out of 4 of these design families that you see up on the screen right now. So just to go over these very quickly, we have the Xpedition Enterprise PCB Design Tool. So that's what we're going to be driving all of our simulations from today. It's a very capable, very high horsepower PCB design tool that allows users to complete their designs very quickly with high quality. And we can ensure that high quality and yield through running HyperLynx, which you see on the third blob there, which is a PCB analysis and verification tool. So within the Xpedition workspace, we will be able to run some HyperLynx rules in order to find certain issues that can cause EMI or perhaps voltage distribution problems on your power supply network. Okay. Also, we will be running some Valor rules, and Valor is on the end spectrum of the printed circuit board design cycle, and with Valor we can actually run PCB assembly, test, and manufacturing checks. So again, show how we can pick a checklist of those issues that we would like to check and then run those directly in the HyperLynx tool. Right, so what we will not be talking about today is pads. And pads, I'm assuming most people might have at least heard of pads, is a long-standing tool that is great for project-based or desktop-based PCB design solution. A lot of customers that I work with are using pads to design high-end printed circuit boards with very high-end technology. It just doesn't include data management capabilities that Xpedition might, or team concurrency, or some of the higher-end functionality that you may need. So a lot of people might wonder, why do we need to run all of these simulations, all of these checks? Why do we have to do any other simulation other than what we do in a standard printed circuit board DRC, running our design rules against what we've actually done in our design? And this little graph just does a good job of showing how PCB systems are continually being more complex as the years go. So the main takeaway from this chart is that red line. It's just showing the average leads per square inch is continually to increase. Okay, so this can cause for a lot of issues. If we're having more and more leads per square inch, we're having more and more vias, potentially more and more power planes. It can add complexity a lot to your system very quickly. So it's imperative to be able to run different types of rules that would not normally be checked just against your design rules. Okay, so a simple example of this is a trace crossing a gap in a reference plane. Very easy to flag that type of issue in the Xpedition and HyperLynx DRC space. Okay, so that can save a lot of time from manual inspection at the end of your design and during the design review phase. It will be able to allow you to quickly identify that and hopefully change that directly in the layout tool. Okay, so here is just a list of what we can actually do in the Xpedition layout space. What simulations can we do in Xpedition? So there's essentially 3 main families of tools that we can invoke directly within the Xpedition layout space. And those are HyperLynx DRC, HyperLynx PI, and Valor NPI for manufacturing checks. Okay, so if you're unfamiliar with HyperLynx DRC, I have done a few webinars in the past on this. There's a lot of good information on the web. But what it essentially is, it's a graphical rule checker that can check for certain things in your design that will cause EMI, SI, or PI issues, or have the potential to cause those issues. Like I said, a trace crossing a gap, as we can see in the bottom right-hand side of the slide here. That's an easy way for the return current path to have to find its own path across that gap or around that gap in that reference plane, making the potential for radiated emissions and some EMI issues that we might see. Okay. SI checks, we can make sure that your impedances are being met correctly for differential or single-ended nets. And then for PI checks, we can also have capacitor placement for your power planes in order to ensure that they're nice and quiet and steady power planes. Okay, so also we can run HyperLynx PI, which allows you to check for DC drop on your respective voltage planes or power planes. Okay? So we can actually define which power planes, which signal pin is the source pin onto that power plane from your voltage regulator. And then we are also able to actually define the sinks, or the actual components that are sinking current off of that power plane. We can define all of that and have constraints for maximum allowed voltage drop, maximum current density for your vias, and then the actual current density throughout your plane. All right, so we're able to visualize all of these directly in the Xpedition Layout space once we have simulated that. And the last family of checks that we'll be talking about is Valor NPI for design for manufacture. Okay, so this is on the back end of the cycle of printed circuit board design, and we can check for fabrication issues, assembly and test, any HDI issues that might be involved, and then flex and rigid flex specific checks for manufacturing. All right, once again, I do not see any questions in the chat box. That's totally fine right now. But if you do have questions, please feel free to type those in there, and I'll hopefully get to those. I just wanted to talk a little bit further about HyperLynx DRC, because it is the one that most people have questions on. And again, I have talked about this in the past, so there's a webinar on this if it sounds interesting. What it does is it automates design checks, eliminating errors for manual inspection. So this can help with your design review process, where you have your EMI expert going layer by layer on and checking EMI issues. Okay, so this can reduce days of manual design checks to just a few hours. It includes built-in rule checks for EMI, SI, and PI. Okay, so these would be items that are not quickly or easily simulated. That's why this is a graphical rule checker. It's a lot easier to check for a trace crossing a gap in a reference plane instead of actually simulating the return current path of all nets in your design. Why this is powerful is we can actually customize all of these different rules and tailor them exactly to the technology that you're working with, or potentially creating company standard checks. Okay, so I'll show that we can actually import rules that have been predefined from other HyperLynx DRC projects, making you really easy and really quick to go ahead and start the simulation, import the rules, and not have to mess around or adjust any of the tolerances that we have predefined. All right, so as far as actually running the checks directly within Xpedition, it's quite easy. If you have the correct licensing, which I'll talk about in just a second, all we have to do is invoke the analysis control dialog. All right, the analysis control dialog you can see in the top right actually allows us to invoke the respective tools that we're trying to simulate with. So you'll see that we can actually start the HyperLynx DRC client as well as the HyperLynx PI client directly within that analysis control dialog box. In here, we have quite a few things that we can actually adjust. Okay, so as in the normal HyperLynx PI tool or the HyperLynx DRC tool, we're actually able to select which rules we want to have run, as well as on which nets. And then we are able to even adjust some tolerances directly within this analysis control dialog box. All right, so once these simulations have actually run, the Hazard Explorer allows us to see all of the information for any errors that might have been found, and actually click on those errors and cross-probe directly into the layout tool. All right, so if you're unfamiliar with the Hazard Explorer, I'll be talking about this during the demo portion, but the Hazard Explorer is a great cockpit that allows you to see your batch or online DRC issues while you're actually routing the board. So if you're unfamiliar with that, I would highly recommend playing around with the Hazard Explorer. It's quite powerful, and I'll show a little bit of tips and tricks on that. Just a general workflow of how this might be productive and allow you to check these issues very quickly is, first, in Xpedition, we're going to place and route the PCB using the design rules directly from the constraint manager. So Xpedition is a correct by construction routing environment. So any of those rules that we have defined in the constraint manager, we're going to be able to actually route to all of those direct constraints that you've entered in that constraint manager. Then we might want to run some HyperLynx DRC rules. So even if you only have potentially even a quarter of the board routed, maybe a half of the board routed, or just your DDR nets, for example, we can actually run HyperLynx DRC directly within that tool halfway through the routing cycle. Okay, so as soon as you route your DDR nets, we can quickly run a HyperLynx DRC check on there to see if there's going to be any EMI issues or if they're meeting all of their impedance requirements very quickly. So we can run that, mark those off as completed, and then just keep on moving out and routing the design and running more HyperLynx DRC rules while we route those other traces. All right, so the next thing we might want to do is actually analyze the voltage distribution network, and we can do that with that HyperLynx PI DC drop directly within Xpedition. So I'll show how we can define which power plane we want to simulate, what those syncing and sourcing pins are for that power plane, and then actually visualize the voltage drop in the 3D Power Scope tool. And then the last checks that we'll be talking about is how we can actually run Valor NPI. So Valor NPI is slightly different than HyperLynx PI or HyperLynx DRC within Xpedition. We do drive this a little bit from the constraint manager. And what we do here is we select which cockpit and checklist you will be using. So cockpit and checklist, those are both Valor NPI types of files that we would have to point to. So the checklist is going to point to the air rule file that Valor NPI uses and checks. So these rules do all have to be set up within the Valor NPI workspace. But once those have been set up, we can easily point to those in the Xpedition constraint manager and run all of those rules on our printed circuit board. Okay, just some quick advantages on why this might be a preferred workflow and allow you to quickly identify issues is we can run those simulations directly in the layout environment. This allows designers, printed circuit board designers, to point to these rules and run them easily, often, and early in the design cycle. Okay, so one major advantage of HyperLynx DRC in specific is that you can work together with your design review team to develop your constraints on what you want to check in these types of EMI checks. Okay, so the designer can actually just point to these rules that have been predefined with your company standards or perhaps a technology standard that you've developed, and then run those rules directly on the layout. So they don't have to be an EMI expert to run these types of rules. The Hazard Explorer, as shown right there on the right, allows us to see and fix most issues directly in the layout phase. So this specific example that it's showing is the via current is too high for this net. You'll see that it shows a description as well as the net, what type of via it's using, and the actual simulated current that's running through that via. Okay, so it gives us a lot of great information in that Hazard Explorer. We can generate a report and then cross-probe directly into the layout tool. And the last advantage that I point out here is that it allows us to perform all of the simulations within this integrated environment. We don't have to be going off into separate simulation tools, importing the design file, setting up the simulation status, and then simulating that design. A quick blurb about licensing. The licensing is required for all analysis done in Xpedition Layout. Okay, so if you're running HyperLynx PI rules, you'll need that HyperLynx SI or PI license, and then you'll need a HyperLynx DRC or Valor NPI license if you are running those rules. Okay, so that's all I wanted to cover just in the slides. Hopefully I gave a good background on how and why we might want to use this type of methodology. So now I'm going to go ahead and actually hop into the tool and show how we can check some of these common design issues. All right, so I have a design open up in Xpedition Layout right now, you'll see. So just for reference, this is the BeagleBone Black printed circuit board, and this is a Mentor Graphics reference design that can be downloaded from the web. So if you want to play around with this board, please feel free to just Google BeagleBone Black Mentor Graphics, and you'll find a link to download that. All right, so we've gone ahead and routed this board for the most part. Now we want to go and run some HyperLynx DRC checks. That's what we will do first. We'll follow that kind of design guideline on design flow of how to use these simulations directly within Xpedition. Okay, so like it said in the slides, the easiest way to go ahead and do this is go from the Analysis tab to Analysis Control. All right, so that's going to open up the Analysis Control tab on the right-hand side that you'll see here. All right, so you'll see that we have two different analysis tools defined here. We've got HyperLynx itself and HyperLynx DRC. I'm going to click on the down arrow and hit Start Client. This will begin invoking the HyperLynx DRC client. As you'll see, we get a splash screen for what license we want to check out. And I'm going to go ahead and secure the HyperLynx DRC developer license. So this does invoke HyperLynx DRC in the background. This will push all of the design information directly into the HyperLynx DRC tool as well. So you'll see once the tool has actually been started, I can now actually see all of the rules that we can run on the board now. Just to quickly talk about these rules in HyperLynx DRC, if you're a little unfamiliar, is if I hop back into the HyperLynx DRC rules, this is the design space for HyperLynx DRC. It's brought in our entire board, all of the nets, all of the stack up information, all of the traces directly within this environment. So if we wanted to adjust the rules that we are actually going to be running, I can look at these different rules that I have set up within here. All right, if I wanted to import rules, all I have to do is right-click on these rules and import rules from other designs. So I can easily set up a template of rules and then import those into all of my other designs. But fairly simple. This tool uses reference designators to understand all of the components and then understands all of the net information from net naming conventions. All right, if we want to take a look a little bit more at what these rules are actually checking, I can click on the rule in the Project Explorer, and it gives us an excellent description of what this check is checking for. Okay, so again, I'm using the nets crossing a gap. This just shows that we have all of these different tolerances that we can define in the bottom spreadsheet view right here. So we can look, these are all of our different parameters that we can define. So an obstacle length, kind of like a void in this plane, we can define that obstacle length as the value that we choose fit. So right now it's set to 300 mils. If it's crossing over any void for 300 mils, we're going to flag that as a violation for this. Okay, so you'll see I've got EMI, PI, and SI issues. I can take a look at decoupling capacitor coverage. So this talks a little bit about where these decoupling capacitors are going to be and the maximum allowable distance from the capacitor pin to the IC power pin. Okay, so this will affect our voltage distribution network and ensuring that that plane is nice and quiet because there's decoupling capacitors directly next to those IC power pins. Okay, so these parameters that we can set here are maximum search distance. So the maximum search distance is going to be from capacitor to pin of the IC itself that it's connected to. All right, so once we've actually set up the different tolerances on our design here, we can go ahead and run these rules back in the HyperLynx or in the Xpedition Layout space. Okay, so if I want, I can go ahead and just click on the different rules that I would like to check. So this is all done directly within the Xpedition Layout space. I can check which rules I want. I can look for routing layer, the biasing of that routing, making sure that it's actually routed on the correct layers that we've defined. All right, so now once I've got those different rules checked, I can click on Analyze Design, and this will take maybe a minute. You can see down below the status that it's going for. We can actually see status bars as well on what checks they're checking and the percentage of that. Okay, so just a little bit about HyperLynx DRC. We do not have to run any of these rules on all of the nets in the design. We can use something called object lists within HyperLynx DRC to define rules that are only run on certain objects lists. For example, if I wanted to check the impedance of just all of my DDR nets, I can create an object list for just DDR nets and then define these rules to only run on that object list. Okay, so very simple, very easy to set up and only have run on the issues that we want to have run. Okay, so it looks like we have finished our analysis, and these are color-coded, so you'll see if there's any red checkboxes, that means there's some errors been found, and green means there has not been any errors found on that particular rule. All right. So what I can do now is I can click on the Hazard Explorer. Again, like I said, the Hazard Explorer is a very powerful dialog box that allows us to see all different types of rules that have been checked and if there's any violations. So you'll see I've got, in the Hazard Explorer, I've got different tabs. I've got an online, as in online DRC, which will actually show us different types of DRC issues for component errors. If there's any type of clearance error, I can actually look at the description. So for example, this P6 reference designator is violating a placement outline to board outline violation. Looks like it's because there's a little bit of an overhang and it is a connector. So we can easily ignore that, put a comment in there, or say accepted. All right, so like I said, we've got normal DRC such as online, batch, and a little summary. Now I can look at my HyperLynx DRC rules that we just ran. Okay, so I clicked on the HyperLynx DRC tab, and this will actually show me all of the different errors that I've had in that HyperLynx DRC simulation. Okay, first one thing I want to talk about is setup warnings. So, for example, this differential impedance rule has set up just because we didn't set up our constant nets or define our differential pairs correctly in the HyperLynx DRC rule. So this just gives us a good overview if anything has failed and for what reason. Okay, just some general things. I can click on my different checks that we checked, and it will show all of the errors that it found. Okay, so in parentheses, you can see the number of violations that was actually found during that simulation, and I can actually click on all of these different, and it will select and actually zoom in onto those areas of the board where that happened. Okay, so the Hazard Explorer allows me to select these different options, which will fit selected or actually cross-probe directly into that layout tool or highlight them. Okay, so I prefer having on fit selected, so as soon as I click on one of those, the screen is going to directly go over that area and highlight that trace. Okay, so in order to make these a little bit easier to work with in C, I do want to offer some tips and tricks while using the display control in conjunction with the Hazard Explorer. Okay, so I have worked with a lot of customers that get a little intimidated by the display control just because there is so much information going on within here. Okay, so if I have this section tabbed while I have my Hazard Explorer, this can be a very effective way to easily identify the issues that I have in my board. Okay. So the first thing about the display control is that this is searchable. Okay, so if I just click my mouse exactly where it is right now, which is right to the right of that minus sign in the display control, I can click there and start typing in what I want to find. Okay, so for example, I know that I love this dim mode option, so I can just search for that and find that dim mode. If I know that I'm going to be using this all the time, I can right click and hit add to favorites. I'll do that with transparency as well. Now after I've added this to my favorites section, it's going to be in favorites under the edit tab. So you'll see I've got graphics mode, dim mode, and transparency set on. So if I have my different net selected from the Hazard Explorer and I turn on highlighting in the Hazard Explorer, so you'll see in my icon I can toggle a highlight, and if I have something highlighted I can dim everything else that's not highlighted in this design. All right, so very easy. I can highlight that directly from the Hazard Explorer and then use this dim mode option to dim everything that's not been highlighted. Okay, so this very easily allows us to see, identify what happened, where that error is, and hopefully identify a solution for it very easily. All right, so here, for example, is an acute angle violation. If we're having an acute angle on those traces, it's going to identify the net that's has been routed in that acute angle. It actually gives us the degrees of the angle that it's been routed in, and then again identifies exactly where it is. Okay, so you can see there's just most of them look like vias going directly to the component pad, a little breakout via, then routed just 90 degrees or greater, or after that. Okay, so within here, what we can do in the display control is I'll go all the way out, and we can actually see that there's a lot of different columns within here. So the last two that I want to talk about are accept comment and accept by date. So directly within this Hazard Explorer, I have the ability to just click on the accept selected hazards icon, and that's just going to give me, it's going to highlight this in green and allow other users to know that this has been accepted, whose it's been accepted by. So you'll see that my PC name on there, as well as a timestamp. Okay. Also, I have the ability to actually accept and add a comment. So if I click on the accept with comments, I can enter a quick comment. Accept it, and we'll see that we have a comment that's been generated in that last column here on that particular error. Okay, so again, this is the exact same rules that it would be checking in HyperLynx DRC, and we can go ahead and look at all of these errors, cross-probe directly within the layout tool, and generate a report after we accept or add comments to these different ones. Okay, so if I want to generate a report, I can have a few different options. I can report the selected hazards that I have selected here, or I can just have a report of all of my different hazards. All right, so I'm going to go ahead and generate a report for all hazards, and as you'll see, it creates a text file for us. It gives us the actual violation that we're looking at right now. So this is only for the acute angle. Great text file here for design review to quickly generate a report on some issues that we might want to take a closer look at. All right. So an easy way, if I want to select a trace crossing a gap, I can very quickly look at that trace. And I'm going to unlock it because it is locked right now. And you'll see that it still highlights the reference net that it's looking at. So you'll see if I turn on layer 2 and 5, because it shows that we've got their signal layers on layer 6 and the reference layers on layer 5, we can actually see exactly where that trace is crossing the gap. Okay, so I could try and do some push and shove out of here to try and fix that issue. But we'll see that that's going to be a difficult issue to solve because we have traces crossing these two gaps in these power planes. So maybe looking at a different routing methodology to fix that issue. All right. Okay, so we've done our HyperLynx DRC check. Now I'm going to hop back into the display control or the analysis control. First, I'm going to terminate the HyperLynx DRC client. And you'll see that it closed it on my Windows taskbar if you notice that. And now I want to actually run some HyperLynx PI checks. Okay, so just like we did on the HyperLynx DRC, I'm going to start the PI check. It's going to go ahead, check out an available license for HyperLynx PI, and then allow us to start looking at our power planes that have been defined. All right, so we have all of our power planes defined in the constraint manager. You can do that by going edit power nets, and you can define which power nets or which nets are actual power nets. Okay, so you'll see it brings all of this up. Again, I'll turn everything on for us real quick. And if I select one of these power nets, it will actually, again, kind of highlight that in the design workspace. I, again, will turn on that dim mode just because I really like that feature. I can select any of these power planes and kind of visualize exactly where it is on the board very easily. All right, so I'm going to take a closer look at my VDD 3.3 volt. And we have a couple of different settings that we can set up directly within this dialog box. So we can set the voltage drop that we want to have as a maximum threshold. So it's a 3.3 volt power plane, and the maximum allowable voltage drop that I want to allow is only 100 millivolts. So I've set the maximum voltage drop threshold to 3.2 volts. Via current, I've set to 1 amp, as well as the current density threshold for that milliamps per square mil. All right. So now what I need to do, I can simulate multiple power planes at once just by selecting on different boxes. That'll take a little bit longer, so I'm just going to only simulate this 3.3 volt source for the time being. What I do here, just like we do in HyperLynx PI, if you're familiar with that methodology, is I'll assign these PI models. Okay, so this will bring up the Assign Power Integrity Models dialog box. And what I want to do first is I want to filter by power supply net. All right, so if I just type in my 3.3 volt source and filter, now it's only going to give me the reference designators as well as the pins that are defined on that power plane. Okay, so it knows from pin connectivity directly from the layout tool which pins and which components are connected directly to these power planes. All right, so to simulate correctly, first I'm going to select pin 4 of U7. That is my voltage regulator. So I'm going to assign a VRM model, a voltage regulator model. I'm going to assign that quickly. So I can decide the voltage as well as the parasitics that are associated with this component. Okay, so I'm just going to assign a 3.3 volt source and hit OK. So you'll see now in the model section for that component, it gives us that we're at 3.3 volt, 1 milliohm, and 30,000 nanohenries. All right, so now to actually assign DC sync models, what I can do is select the different pins on these components and just hit Assign DC sync. What we're doing here is we're saying that these pins are syncing current off of this power plane. All right, so what I can do here is I can apply a current sync to each one of these component pins, or I can assign it as the whole group. So if I want to say this entire component as 1 is pulling 1.5 amps, let's say 1.6 amps, I can hit OK, and the tool will automatically go ahead and determine how much current is being drawn off of each pin. All right. What I can also do is I can group select this entire U5 as well as U4 and U3 and hit Assign DC sync model. And if I don't want all of these to be pulling off 500 milliamps, I can just hit OK on each sync, and you'll see that each one of these pins is now pulling 500 milliamps. All right, so very easy. That's essentially all the setup that we have to do right now for this PI simulation. Okay, I'm going to hit OK. And once we've done that, I'm going to hit Analyze Checked. So this will start running that DC simulation. You can see down below at the bottom of the analysis control box that it's running that DC drop simulation and should very quickly be done for us. Okay, so once it says simulation complete, there's a couple of different things that we can do. The first being, I want to actually look at the 3D representation of that power plane. All right, so I'm going to load in those results that we have, and we'll see that we get a 3D representation of this power plane. All right, so this is the exact same dialog box that we get when we're simulating these DC drop simulations directly in the HyperLynx DC drop tool. What this is the 3D representation of our voltage plane. All right, so if I hold the control mouse button up at the top, we'll get some useful information about this power plane. Okay, so we get the layer that it's on, the XY location reference to the actual layout design, and then the voltage at that point. Okay, so obviously the higher the point is in the 3D space, so you'll see in 3D, the higher this point is the higher the voltage is. Okay, so when I hold the control key, as well as hover my mouse over there, it gives us the voltage at that specific point. So we can see the lower and lower I get, it actually changes and shows us what that is, that value is. All right. There's a couple of different things I can do here. So that's DC drop. If I want to put in a threshold, let's say I want this to be no less than 50 millivolts of voltage drop, I will type in 3250 millivolts, and it's automatically going to place this little hovering icon showing that anywhere below this gray icon, we're going to have voltage drop issues. So that might be a little too large. So I'll make this a 75 millivolt voltage drop, might be a little too large for us. But it looks pretty quiet for us. We defined in the constraints that we wanted just 100 millivolts of voltage drop, and if that's what we follow, it looks like we're passing that for the voltage drop simulation. Also within this, we have the ability to turn off the different layers that this has been routed on. So we can just see the voltage on those specific layers. So these might be the vias, it looks like, as well as just layer 5, and then just layer 6. We've got just a few sections. So most of this is on layer 5 of our design. That way we can easily go back into the layout tool and look at this power plane. All right. Also within here, I can actually look at my via current. So if I go to my visual options and select DC via current, we will see all of the different vias that have a high current on them. So you'll see layer 6 via has 13.3 amps running through that. So we might want to take a look at that. It looks like that is where our voltage regulator is actually connected to it. So we want to go into that, look at that via, make sure the pad stack's big enough to handle that type of current. Also, we can actually look at the DC current density. And again, this is a 3D representation of that plane showing where the higher current density is on that plane. All right, so again, it's all mostly focused on where that voltage regulator is, and we can easily identify that issue on the printed circuit board. Okay, so I can understand where that is on the board. U6 is over here, and kind of identify an issue for that. All right, so that's a 3D representation. We also have the ability to look at the Hazard Explorer, and this will identify via currents. Okay, so this would be helpful within that 3D representation to see where those vias were, and then I'm able to actually click on these vias exactly where they are. Okay, so again, the useful information that it gives us is the actual via that it's using, the net that it's attached to, which most of them should be that 3.3 volt source, and if we want to accept or reject these changes. Okay, so if I want to accept these via currents as being acceptable, just 1 amp, that should be fine. All right, so really easy, we can see that this current on this via is 13.3 amps. And here is U5. Okay, so that's our voltage source. And we can see that that via is highlighted in red. So we want to take a look at that and fix that issue somehow. All right. Okay, so the last thing I want to check is some Valor NPI rules. And like I said, Valor NPI is slightly different than both of the HyperLynx checks that we've both done already. If I start the constraint manager, which the constraint manager can be started just by clicking on this icon for the constraint manager, or if I go set up constraint manager, that will launch this tool. If you're unfamiliar with this, this is a spreadsheet-based design rule entry system. Very easy to define all of your design rules that you're going to be routing and placing to in this dialog box. I don't have enough time to go through a lot of here, but this controls all of our net information as far as the length, matched group, differential pairs, and the topology that it's routed out. So all that I have to do within here is actually go to the tools menu, Valor NPI and select which design rules I want to run against this design. Okay, so if you are a Valor NPI user, you should be familiar with the design center that we have to select first, as well as the checklist. So the checklist references your error rules file that you've defined in Valor for your constraints and allows us to run those directly within here. Okay, so all I have to do is select those design center and checklist in that constraint manager and close this out. Okay. All right, so once we've defined which checklist we want to use for our Valor NPI rules, all I have to do is hit Valor NPI BFF, and this will invoke Valor NPI as well as use that checklist to check for all of those issues. All right, so what this is going to do is it's going to create an ODB++ file. So you'll see right there, we've got an ODB++ output being generated. It's creating this file for us and pushing it over into Valor, running those rules, and then giving us the errors back again, just in that Hazard Explorer. Very easy to work with. All right, so it pops open the license configurator. I've got a Valor NPI license that I would like to use. Just hit OK, and that's going to start running those rules for us. So like I said in the slides, you do need valid licensing for all of the checks that you check within here, be it HyperLynx DRC, HyperLynx PI, or Valor itself. All right, so we should get a dialog box when the rules have completed for us. All right, so Valor NPI process is complete. Go to Analysis, Hazard Explorer for results. Okay, so just like we've done with all of our other checks, I can click on my Valor NPI checks. So within here, we're checking, again, manufacturing issues. So if we have issues such as stubbed vias or no thermals on our connections to our power plane, that's just something I've defined in my error rule file in Valor NPI. Okay, slivers, we can check on those, and it'll, again, cross-probe directly into the layout tool. All right, so just like with all other Hazard Explorer that we've looked at so far, missing SMD clearance on this pin, I can actually accept or reject and add comments. All right, so what we've done so far is we've placed and routed this board. We've ran some HyperLynx DRC rules. We've ran some HyperLynx PI rules. And then we actually ran some Valor NPI rules for manufacturing checks. All right, so that was all I was planning on showing you today. I don't see any more questions in the chat box. I hope it was useful information for you all. If you do have any questions about anything you saw, again, here's my contact information. Please feel free to reach out to me. I'm always happy to answer questions or help you out with anything that you may need. And then the last thing I'd like to point out is, again, save the date for my next webinar. There's going to be multi-board design with Systems Designer and the Xpedition flow. That'll be Thursday, December 6th, same time. So I hope to see you there.